Well, hello and welcome to today's Third Thursday webinar. I am Tom Sandry, and today we are going to be talking about transformer winding resistance testing. Okay, so without further ado, let's get started and take a look at the topics for today's webinar. Today we're going to be discussing why should we test winding resistance on transformers? When should we test? What kind of problems will the test detect? What kind of test equipment should we be using? And are there safety considerations that we need to consider? We will talk about selecting proper test current. And also we will be looking at the interpretation of the measurements themselves. Now, why should we test winding resistance in a transformer? Well, winding resistance measurements in a transformer are of fundamental importance for the following purposes. Calculations of the I squared R component of conductor losses. I squared R is basically the heat losses. Calculation of winding temperature at the end of a temperature test cycle, and also as a diagnostic tool for assessing possible damage in the field. Now, in addition to the obvious faulted windings, such as an open winding or shorter turn, the test reveals more subtle problems. The DC current not only flows through the winding of the device under test, but also through numerous welded and mechanical connections. In the case of a transformer, the DC current must also flow through the offload adjusting switch and the on-load ratio adjusting switch, the load tap changers. Therefore, the integrity of all these components can be verified. Now, regardless of the configuration, either star or delta, the measurements are normally made phase to phase, and comparisons are made to determine if the readings are comparable. If all readings are within 1% of each other, then they are acceptable. Keep in mind that the purpose of the test is to check for gross differences between the windings and for opens in the connections. The tests are not made to duplicate the readings of the manufactured device, which was tested at the factory under controlled conditions and perhaps at temperatures other than those experienced in the field. So, when should we test? Well, one time would be during relocation and commissioning validation. There is risk of damage, and risk of damage is significant whenever a transformer or rotating machine, for that matter, is moved. This is inherent to the typical design and modes of transportation that's employed. Damage can also occur during unloading and the assembly of the transformer. The damage will often involve a current carrying component such as the load tap changers and the ratio adjusting switches and connectors. Damage to such components may result in a change to the DC resistance measured through those devices. Hence, it is recommended that the DC resistance be measured on all load and offload tap positions prior to energizing of the transformer. If the transformer is new, the resistance test also serves as a verification of the manufacturer's work. Installation measurements should be filed for future references. Now, also, the testing should be done as part of a routine or scheduled maintenance interval. Routine maintenance is performed to verify operating integrity and to assure reliability. Tests are performed to detect incipient problems. So, now we know when we should test, but what kind of problems will a winding resistance test uncover for us? Well, let's first look at the ratio adjusting switch, or the tap changers. Contact pressure is usually obtained through the use of springs. In time, metal fatigue will result in lower contact pressure. Oxygen and fault gases, if they exist, will attack the contact surfaces. Additionally, mechanical damage resulting in poor contact pressure is not uncommon. As an example, a misaligned switch handle linkage may result in switch damage when operated. Such problems will affect the DC resistance measured through the load tap changer switch and may be detected through the winding resistance test. Now, the load tap changer contains the majority of the contacts and connections in the transformer. It is one of few non-static devices in the transformer and is required to transfer load currents. In addition to detecting problems associated with high resistant contacts and connectors, many winding resistance test sets will also detect open circuits. This is normally referred to as the dropout test. Load tap changers transfer load and are designed for make before break. They are not designed to interrupt load current. An open circuit would likely result in a catastrophic failure. Now, on installation and after maintenance, it is certainly prudent to verify operating integrity by checking for open circuits. Load tap changer maintenance often involves considerable disassembly, and the winding resistance test will provide confidence in the reassembly. Now, it is recommended DC resistance measurements be made on all on-load and on-load taps to detect problems and verify the operating integrity of the load tap changers and switches. Now, also, the winding resistance test is also very good for unscheduled maintenance or troubleshooting. Unscheduled maintenance generally occurs following a system event. The objective of the unscheduled maintenance is to detect damage to the transformer or possible damage to the transformer, to determine if it is safe to re-energize, to determine if corrective action is necessary, and to establish priority of corrective action. Many transformer faults or problems will cause a change in the DC resistance measured from the bushings, shorted turns, open turns, poor joints, or contacts. Hence, the information derived from the resistance test is very useful in analyzing faults or problems, complementing information derived from other diagnostic tests such as frequency response analysis or dielectric response analysis or power factor testing. Also complements DGA and other measurements. The winding resistance test is particularly useful in isolating the location of a fault or problem and assessing the severity of the damage. Now, when looking at micro-ohm meters, okay, let's take a look at the test equipment. When looking at micro-ohm meters and what are designated as winding resistance test sets, at first glance, these two test sets appear very, very similar to one another. After all, both sets are used to measure very low resistances, right? Well, it is true that both test sets are used to test very low resistances, and both test sets use an applied DC current to measure these very low resistances. But in actuality, that is really where the similarity between these two test sets end. Micro-ohm meters are well suited for a wide range of applications where measuring the integrity of a connection or bond is required. In these applications, there is no storage of energy in the test specimen. Now, when we look at windings of a large motor, or in our conversation today, a transformer, we need to keep in mind that these windings are essentially large inductors. The higher the voltage and the larger the MVA or capacity, the higher the induction and hence a potential hazard when applying DC test currents. Standard micro-ohm meters simply do not provide the added safety features offered in a dedicated winding resistance test set. Such test sets might be the Vanguard model WRM10, the WRM40. Another very popular brand is the Protec. For instance, maybe the model WR50, the WR14 units. Again, manufacturers such as Megger also makes test sets of this type that are dedicated winding resistance test sets. So when doing windings of transformers, particularly large transformers, where the DC will create a magnetic field in the winding and that winding will hold the energy in the form of a magnetic field. This is a safety consideration, and this is where a dedicated winding resistance test set becomes very, very important. We should not be using the standard micro-ohm meters. They're not equipped with the safety features in order to deal with the stored magnetic energy of the winding. So let's talk a little bit more on this subject. Let's talk about this thing called inductive kick. Okay? Now, when voltage is placed across an inductor, a counter voltage equal in potential but opposite in polarity to the power source forms across the inductor to prevent current from flowing. This counter voltage cannot be sustained and decreases exponentially until it drops to 0 volts. As the counter voltage decreases, the current increases until it reaches its maximum level. So as the current flow through the inductor increases, it energizes the inductor coil, causing a proportional magnetic field to build. If the power source is removed and a current path is provided to enable the inductor to de-energize, the magnetic field around the coil collapses and induces a voltage in the opposite polarity as when it was energized, as this animation had shown us. So let's just go ahead and play that animation one more time. So when we start to energize, we're pushing current through. Initially, the inductor is trying to oppose the change in current flow. It cannot sustain this. Current begins to rise, but this magnetic field is being produced. Now, the voltage induced into the coil, as we say, cannot be sustained and decreases exponentially to 0. In the demonstration video that we are watching here, the current from the de-energizing coil flows through the neon bulb and causes it to flash when we go ahead and change the switch from position A to position B. Now, this video illustrates for us the inductive kick of an inductor. Now, the safety consideration that we're talking about when using a non-winding resistance test set, like just a standard micro-ohm meter or inductor, is these devices do not typically have the discharge mechanisms to be able to safely bring down these large magnetic fields and discharge the energy that's stored or the magnetic field that was created on the winding. A dedicated winding resistance test set offers this extra safety feature. So when we energize and we obtain our reading, the magnetic field is created because it is DC. It is not collapsing. It's DC. It's only going one direction. So the field is created. When we conclude the test, a winding resistance test set, dedicated instrument for this purpose, will then switch, ground, and discharge the magnetic field safely through the test set. Without this feature, A technician could potentially grab the test leads, and in the process of disconnecting, the magnetic field is collapsing, causing large arc flashover, and again, is a safety consideration. All right, let's move on from the test equipment now. Moving on from the test equipment, let's look at the safety considerations, okay? One, we need to ensure that the test leads are securely attached to the windings of the terminals. Do not operate any instrument control which would open the measured circuit while the DC current is flowing during the winding resistance test, and discharge the winding before trying to disconnect or handle the circuit. Do not disconnect any test leads while the DC current is flowing, and ensure the winding is discharged again before handling. When terminating the test, wait until the discharge indicator on the winding resistance test set goes off before attempting to handle the test leads or to remove the leads. Now, failure to take appropriate precautions can result in a hazardous potential, which could be harmful to both the personnel and the test equipment. A dedicated winding resistance test set is designed to minimize this hazard. I need to stress this point. When using a dedicated winding resistance test set, users and test equipment are protected by the shutdown circuit safety features built into these test devices. Any inadvertent disconnection of the test leads or loss of power to the instrument will safely discharge the energy stored in the test sample. All right, let's move on now. And staying on the focus of safety considerations, let's talk about AC induction. Now, when a transformer is located in an AC switchyard in close proximity to energized conductors, it is quite possible an electrostatic charge would be induced onto a floating winding. This hazard can be eliminated by simply tying all the windings to ground. However, to perform a winding resistance test, only one terminal of any winding can be tied to ground. Grounding a second terminal would short that winding, making it impossible to measure the resistance of the winding. Two grounds on the winding under test would probably result in measuring the resistance of the ground loop. Two grounds on a winding which is not under test will create a closed loop inductor. Because all windings of a transformer are magnetically coupled, the DC test current will continually circulate within the closed loop inductor, the shorted winding. The instrument display would probably not stabilize, and accurate measurements would not be possible in this test configuration. Now, it does not matter which terminal is grounded as long as there is only one terminal of each winding tied to ground. When test leads are moved to subsequent phases or windings, on the transformer, it is not necessary to move the ground connections. Ensure the winding is grounded prior to connecting the current and potential test leads, and when disconnecting the leads, remove the grounds last. All right, now let's talk about selecting the proper test current. Again, in these winding resistance test set, it gives us the ability to set different test current levels. So how do we know which one we should use? Well, transformer manufacturers typically recommend that the current output selected should not exceed 10% of the rated winding current. Okay, the recommended current for test purposes should not exceed about 10% of the rated winding current. This could cause erroneous readings due to heating of the winding. Example, a transformer rated at 1,500 kVA, single phase. The rated current of the 35 kV winding is 43 amps. Therefore, the test current in this example should not exceed 4.3 amps. Always choose the highest current output possible for the expected resistance value. All right, next let's take a look at measurements. The recommended measurement method. Now, in the diagram here, let's kind of try to walk through this. A lot of these winding resistance test sets are two-channel instruments. Okay, so for best application, let's take advantage of the two measurement channels and let's measure the high side and low side winding simultaneously. To do this, we have to create a current loop. Current must enter the high side winding, then go to the second or the low side winding and return back to the test set. So let's trace out the path of how we accomplish this. So for instance, let's take the C1 and we will connect it to the high side winding. The current goes down through the winding, up through the second terminal or bushing. Now the test set will provide a jumper cable. We take the jumper cable, we jumper it over to the low side winding. The current now is capable of going into the low side winding, through the winding, back up through an adjacent bushing. We now take the current minus lead, connect it to this bushing, and bring the current back into the test set. Hence, we have a nice large current loop now. Now we hook up our potential leads. So basically we've got 2 voltmeters in here. We take our first potential channel and we go ahead and connect to the bushing where the current is entering into the windings. Okay, and the second potential lead goes to the other bushing. So basically, effectively, we're making a measurement across a voltage drop measurement across this winding. And then we just repeat this on the low side winding. We basically connect one potential channel to one bushing. Effectively, it's electrically the same as connecting it to this point on the winding. And we connect the other potential channel to the other bushing, which effectively is measuring on the other side of the winding or the voltage drop across the winding. So now the test set is capable of providing us a resistance measurement on both windings during the same test sequence. We apply a known current, we measure the potential drops, the instrument calculates and provides the winding resistance value. In today's session, we're going to go ahead and learn how to do a winding resistance test on a transformer winding using the Protec WR50-12 model. This instrument really functions like any other micro ohm meter or low resistance ohm meter. It just has additional safety features built into it for testing transformer windings. Now, like any low resistance ohm meter, the way this measurement works is through the simple use of Ohm's law. We apply a high test current, 10 amps, possibly up to 50 amps. The current flows through the winding that we wish to measure. Next, we use a voltmeter, and we measure the voltage drop across that winding. Through Ohm's law, we know if we take the measured voltage divided by the injected current, we will then end up with the resistance or ohms of the windings. So here we are at the transformer ground strap connection point, working from our low potential to our high potential. Let's go ahead and get a good earth ground established by clipping our lead onto the transformer's ground strap. So let's take that earth ground that we just established and connect to the ground post of the test set. Now we're about to test a non-energized delta Y transformer that's just sitting in a storage yard. The first demonstration, I'm going to show you how to use the 2-channel configuration on the Protec test set, where we will be able to test the winding resistance of both the primary and secondary winding simultaneously. To do this, remember, we first have to inject current and have current flowing through both windings and back to the test set. Therefore, we're going to take our positive current lead and connect it to H3. As we can see in this diagram, current will flow across through this primary winding and out H1. In order to get current into our secondary winding, we will take the jumper lead supplied in the Protec kit and we will connect the jumper from H1 to X0. Now current will flow up through H0 through this winding, and then the black current return lead we will connect to X1 and bring that back to our test set. Now current will flow through the primary and secondary winding simultaneously. Our next connections will be to connect potential channel number 1 across the primary winding. So we would connect the potential channel red lead to H3 and the black lead to H1, measuring the potential drop across this winding. On the secondary side, we will take our channel 2 potential test leads and we will connect the red lead to the X0 and the black lead to the X1, measuring the voltage drop across our secondary winding. Now before we actually start our test, let me draw your attention to 2 very important safety features on this test set. The green LED will illuminate when it is safe to make connections or when it is safe to disconnect any lead from the windings of the transformer. When current is applied and is flowing through the windings, the red LED indicating current on will illuminate. Do not attempt to remove a lead when the red lamp is on. To perform the test, make sure that both boxes of channel 1 and channel 2 are checked so that we're actually measuring both channels simultaneously. If you wish, go over to the setup and you can start setting up some general information for the test. Typically, I will go to configure. Sometimes it's helpful to use a stylus when working this instrument. And you can see here, channel 1, I'm going to do a delta. Channel 2, I'm going to do a Y. I can change my configurations here for various combinations of H1 to H2, H2, H3, H3, H1. We're currently configured for H3, H1, so we'll leave it set there. On the low side, I can do the same, and I can change to numerous different configurations. X1, X2, X2, X3, X3, X1, X1, XO, X2, XO, X3, XO. We're going to leave it set for X1, XO. Next, I could go ahead and change the applied current range. And I can apply current, test current, anywhere from 0.1 amps up to 50 amps. For the particular transformer we're testing today, I'm just going to leave it at the 10 amp setting. And I'll also leave it checked for auto close setup. Depress OK.
And we're ready to start our test. So we will hit the start button. The instrument will prompt us that it is charging the windings. The red lamps will flash behind or will illuminate behind the measurements as yet another safety indicator that current is being applied. Caution, do not touch the leads. When the measurement is complete and we have a stable reading, the green lamp will come on, and then the master safe will indicate that it is now safe to remove the test leads. Our measurements on our H3 to H1, as we see, is 222.7 milliohms. Our X1 to XO is 10.419 milliohms. Now, after you've completed the test and you're satisfied with the results, always perform a demag function before leaving the transformer. What we have just done is we fed DC current through the coils or the windings. This will leave the transformer in a magnetized state. Therefore, when we are completely done with our testing, always remember, select demag and start the demag process by pressing start. The instrument has indicated that it has finished the demag process, and we can now hit end, and now we're ready to make our next connection and test our next winding. If we wish to do the remaining windings, we merely follow the exact same procedure, following our diagram, making sure that we have current flowing through the winding we wish to test, jumping it over to the other side winding, flowing through that winding, and then returning back to our test set, and then simply moving our potential leads across those respective windings. Always remember, when current is flowing, never touch the test leads or try to remove the test leads. And secondly, always perform a demag before leaving the transformer. I'm Tom Sandry, and thanks for watching.
So, now we got a glimpse of the more effective use of a dual channel or multi-channel winding resistance test set, and how we can utilize it for more efficient charging, better, more stable readings, and basically just allow us to move along the job, particularly if we've got lots of load taps, settings and everything to go ahead and change. So, little education on how to get the best out of the product. Now, let's talk a little bit about interpretation of measurements. Measurements are evaluated by comparing to original factory measurements. They are also comparing to previous field measurements, which tends to be the preferred or better. As we talked about earlier, comparing to the factory, it is done, but we need to remember the factory is doing this under a controlled condition, the temperatures and so forth that we're experiencing in the field, the winding temperatures when we're doing the testing in the field will obviously differ from the way it was done at the factory. Okay, we are also comparing one phase to another, which is probably one of the best ways to go ahead and look to see if there are subtle issues or problems developing. Now, the latter will usually suffice, the comparing one phase to the other. The industry standard or factory standard permits a maximum difference of 0.5% from the average of the three-phase windings. Now, field readings may vary slightly more than this due to many variables. So it may be difficult for a field test to fall within this 0.5% rule that the factory uses. Now, if all readings are within 1% of each other, then they are acceptable by field testing standards. So again, just to kind of reiterate, at the factory, under controlled conditions, Normally the tolerance is permits 0.5% from the average of all three phases. But for field, there are a lot of variables that can make this very, very difficult. So the accepted for field is, as long as the readings fall within 1% of each other, that would be considered acceptable in a field test. Variations from one phase to another or inconsistent measurements can be indicative of many different problems, possibly shorted turns, open turns, defective ratio adjusting or RA switch or load tap changer, poor connections, brazed or mechanical. The winding resistance test is very useful in identifying and isolating the location of the suspected problems. Now let's talk about some confusion factors that can make the readings confusing to us. And why are we getting this type of reading? So let's go through these confusion factors together. Apparent problems, inconsistent measurements or variations between phases can also be the result of a number of factors which are not indicative of problems at all in the transformer winding. Failure to recognize these factors when evaluating test data can result in confusion and possibly unwarranted concerns. The DC resistance of a conductor, hence winding, will vary as its temperature changes. For copper windings, 0.39% per degree Celsius. This is generally not a significant consideration when comparing one phase to another of a power transformer. Loading of power transformers is generally balanced, hence temperatures should be very similar. However, when comparing to factory measurements or previous field measurements, small but consistent changes should be expected. In addition to loading, temperature variations, likewise resistance variations, can be due to cooling or warming of the transformer during test. It is not uncommon for 1 to 2 hours to pass between taking the first and the last measurement when testing a very large transformer with a load tap changer. A transformer which has been on load can have significant temperature change in the first few hours off load. Now, when measuring the DC resistance of smaller transformers, care should be exercised to ensure that the test current does not cause heating in the winding. The test current should not exceed 10% of the winding rating. All right, let's take a look at contact oxidation. The dissolved gas in transformer oil will attack the contact surfaces of the load tap changer and ratio adjusting switches. The problem is more prevalent in older transformers and heavily loaded transformers. Higher resistance measurements will be noticed on taps which are not used. Typically, a load tap changer installed on a sub-transmission system will only operate on 25 to 50% of its taps. This apparent problem can be rectified by merely exercising the switch. The design of most load tap changer and ratio adjusting switch contacts incorporate a wiping action which will remove the surface oxidation. Hence, operating the switch through its full range 2 or maybe even up to 6 times will help remove any surface oxidation and can help eliminate this confusion factor when performing your tests throughout the tap changer ranges. Now, a potential transformer installed in one phase could become part of the measured circuit and affect the measured DC resistance of that particular phase. So keep that in mind as well. Okay, ambiguous or poorly defined test data. There is often more than one way to measure the resistance of a transformer winding. For example, line terminal to line terminal or line to neutral. Typically, field measurements are taken from external bushing terminals. Shop or factory measurements are not limited to the bushing terminals, however. Additionally, internal winding connections can be opened. Example, opening the corner of a delta, making measurements possible which are not practical in a field application. Details of these test setups and connection areas are often omitted in test reports, which can lead to confusions when trying to compare test data. So again, for field-related tests, it is always very helpful to put into the comments the test configuration. Did you test using both channels and test the high and low simultaneously? Did you use it as a single channel instrument? What was the temperature of the day? What were the oil temperature or winding temperature? We can get this off the gauges of the transformer prior to starting the test. So collect the data so when we are comparing possibly in the future to a test done on a different day, when we do see variances or differences, we can work our way through this confusion factor. All right, so how bad is bad in these measurements? When a higher than expected measurement is encountered, what does it mean? Is failure imminent? Can the transformer be returned to service? Is corrective action needed? Well, to answer these questions, more information along with some analytical thinking is going to be required. Okay, firstly, have the confusion factors that we discussed been eliminated as the possible cause? Secondly, what are the circumstances which initiated the resistance test? Was this a routine maintenance, or did a system event such as a lightning strike or a through fault occur, resulting in a forced outage? So again, are we testing just because of preventative maintenance, a PM? Everything was working perfectly fine. We brought the transformer down as part of a PM, and now we're questioning the readings? Or was this test initiated due to, for instance, a through fault where there is suspicion that there might be something astray? Is other information available? What is the maintenance history on the transformer? What is the loading history on it? Do we have DGA, dissolved gas analysis data or results? Capacitance, bridge, or excitation current measurements? If not, do the circumstances warrant performing additional tests? Consider the transformer schematic. What components are in the circuit being measured? Has the location of the higher resistance been isolated? How much heat is being generated by the higher resistance? Now this can be calculated, I squared R, using the rated full load current. Is this sufficient heat to generate fault gases and possibly result in catastrophic failure? So again, one of the best ways to determine is this problematic is we now have the resistance value. We can locate on the nameplate the full load current. We can do a little calculation here to determine what is the actual watts or heat that's going to be produced, and will this level of heat be sufficient to generate fault gases within the transformer? That's probably one of the best ways to determine if it's really truly bad. All right, let's review. Measuring a transformer's resistance from one external terminal to another can reveal lots of information about the device. Measurements reveal such things as faulted winding, an open winding, or shorted turns. They can also reveal more subtle problems. Measurements are normally made phase-to-phase, and phase comparisons are made to determine if the readings are comparable. If all readings are within 1% for field application of each other, then they are acceptable. All right, we're going to do something a little different in today's webinar. Okay. As part of our review, we're going to do some review questions, and you're going to get to participate by typing the answer to the questions into the chat function. All right, let's get started. The first question: the risk of damage is significant when a transformer blank changes temperature, is transported and installed, getting regular maintenance, or is grounded. Take a moment, type either A, B, C, or D into the chat function. And the answer is: the risk of damage is significant when a transformer is transported and installed. All right, review question number 2. When measuring the DC resistance of smaller transformers, the test current should not exceed blank of the windings rating. Type in now A for 50%, B for 25%, C for 10%, and D for 75%. And the answer is C. When measuring the DC resistance of smaller transformers, the test current should not exceed 10% of the windings rating. All right, let's move on to question number 3. Which of the following is not a confusion factor when testing the winding resistance of a transformer? A, AC induction is not a confusion factor. B, temperature change is not a confusion factor. C, contact oxidation is not a confusion factor. Or D, ambiguous test data is not a confusion factor. Type into the chat A, B, C, or D. Which is your answer? And the answer is AC induction is not a confusion factor in a winding resistance measurement. AC induction is a potential safety concern when testing a transformer in a yard when it is in proximity to live energized lines. Number 4. When testing large inductive devices such as transformer windings, any old micro ohm meter can be used without any issue of safety risk. True or false? Enter A for true and B for false. And the answer is false. We should not be using a standard micro ohm meter. Again, inductors store energy in the form of magnetic charge. Therefore, when we are pumping DC current through that winding, a magnetic field is being created. The test set needs to have provisions to discharge, to bring down that magnetic field safely, discharging that counter EMF through the instrument and not through a potential worker. Number 5, which of the following is true of a transformer located in an AC switch yard? A, the transformer should not have a winding resistance test performed on it. B, electrostatic charge is induced on any nearby floating winding. C, the transformer should not be grounded. D, when test leads are moved to subsequent phases or windings on the transformer, we need to move the ground connections. So, which of those is the proper statement? Which of the following is true of a transformer located in an AC switch yard? Enter into the chat A, B, C, or D. Enter your answers now. And the correct answer should be B. Electrostatic charge is induced on any nearby floating winding. All right. Appreciate participation today. That's going to go ahead and conclude our webinar. So brings us to that magical time of questions and answers. Again, as always, we thank you so much for attending the Third Thursday webinars. Again, Matt and I really, truly enjoy doing this. All right, let's get to those questions and answers.